if we have a bell-shaped set of data, and you can see in this case, I've got a bell-shaped set of data that I've just kind of randomly picked here. And it's bell-shaped because if you fit a normal distribution curve over top that data set, then clearly it's bell-shaped. I've chosen a dot plot here to kind of make this as clear as possible as exactly what's happening with the empirical rule. Now, it doesn't matter that the data is bell-shaped. Every single data set has a mean and a standard deviation. So if you went through every single one of these data points, added them together, divided by the number of values that existed, you would see that the mean is 45.5, which is what's listed there. And that's right down the center of the distribution, which is always something that happens on a symmetric distribution. Now, also, if you went through and you calculated the standard deviation of all of these data items, it would come out to 3.14, which is what's listed. Now, in terms of the empirical rule, what it gives us is a prediction of what percent of the data lies within certain values. And those values are multiples of your standard deviation. So, for instance, if I have my mean at 45.5, that's what's in yellow, and I take my standard deviation of 3.14, if I add that to my mean, then that gives me 48.64. So this is the standard deviation, the mean plus 1 standard deviation. If I do that again, if I take 48.64 and add 3.14 to that, it gives me 51.79. There's some rounding error, doesn't matter. That's the mean plus 2 standard deviations. So these markings down below are just changing the scale of the axis to the mean and the standard deviation. So just multiples of that standard deviation. Now, what's important is if you have a bell-shaped distribution, which we do, then what the empirical rule says is that within 1 standard deviation, so for all these values, I've highlighted them in blue, that are within 1 standard deviation, so they're within the first 2 green marks. There's supposed to be about 68% of all the data values. Now, there are 250 data items in this data set, and it's very nicely told us here, 164 of those happen to be between those two, within that first standard deviation. And that works out to about 65.6% of the data. So that's pretty accurate. So it's about 68%. And then it says within 2 standard deviations, you're going to find about 95% of the data. And it's gone through and calculated the number of values that are within 2 standard deviations here. And there's 236 of these dots out of the 250, which works out to a percentage of 94.4%. And then if we go to 3 standard deviations, it's supposed to be about 99.7. In this case, the way the data is created, it works out to 100% of the data. But, you know, in general, 99.7 is what you would count on there. So that's what the empirical rule says. Just it predicts for us the percent of the data in a bell-shaped distribution that's going to be within a certain number of standard deviations. And because it's symmetric, you can even take the 68% that's supposed to be within 1 standard deviation and divide that in half and say that it's about 34% on the right-hand side or 34% on the left-hand side. So it's symmetric, you can do that sort of thing. Now, let's go to a question here. So I've written down the empirical rule. So 68% of the data is supposed to be within 1 standard deviation of the mean, 95% within 2 standard deviations, and so forth. Now, this question says the heights of American adults are normally distributed with a mean of 177 centimeters and a standard deviation of 7.4 centimeters. Use the empirical rule to find the range of heights that contain approximately 68% of the data, 95% of the data, 99.7% of the data. Now, it's no mistake that these values match, because what they want us to do is essentially If they're asking for 68% of the data, the two values that surround that, we need to find the two values within one standard deviation. So how do we do that? Well, you just think that there's this hypothetical normally distributed set of data somewhere, okay? You don't have to see this bell curve, but it helps to think about it. The mean of this bell curve is given as 177 centimeters. That's in the center of our distribution. Then we have a standard deviation of 7.4 centimeters. So I can start marking off these values by adding and subtracting that standard deviation from our mean. If you need to grab a calculator for that sort of thing, no problem. So 177 plus 7.4 gives me 184.4. And if I subtract 177 and 7.4 from 177, that gives me 169.6. So within these two values, according to the empirical rule, so this is one standard deviation to the left. So, sorry, this is my mean. So this is one standard deviation to the left of the mean, and this is one standard deviation to the right. So within those two values, 169.6 and 184.4, I should see about 68% of my data. That's what the empirical rule is telling me. And the same is true of 95% of the data, except we have to go a second standard deviation out because it's two standard deviations for 95% of the data. So I just go another standard deviation, and to do that, I would take the 184.4 that I've gone so far and add 7.4 to that to get 191.8, and then 169.6 minus the 7.4 would give me 162.2. And so now what the empirical rule predicts is that within these two standard deviations, this amount of area, or the hypothetical number of data points that are between those two values in our data set, is going to be about 95% of our data. So that is our answer here. So 162.2 and 191.8. Then lastly, I think you can catch a pattern here. We basically just need to walk out one more standard deviation to figure out the values that have 99.7% of our data within them. So we take the 191.8 and add to that the 7.4. So that upper limit is 199.2. And then if I take 162.2 minus the 7.4, that gives me 154.8. And that's how we use and interpret the empirical rule.